So let's resume our discussion of Chapter 7. When we last left off, we were discussing redox reactions and balancing redox equations. So what I would like for you to do now is, just like we've done in previous problem-solving sessions, I'd like you to assign oxidation numbers to each atom in the following redox reaction. Identify the oxidizing and reducing agent, and then write the oxidation and reduction half reactions, noting that electrons are conserved in redox reactions. So let's take about 5 minutes and work through this example. And again, don't be shy to message me in the chat with your proposed oxidation and reduction half reaction and your proposed number of electrons transferred over the course of this redox reaction. And we'll discuss this example in about 5 minutes. But if you have any questions at all, don't hesitate to type them in the chat or unmute and ask your questions verbally. And we'll go through this example together as a group in about 5 minutes. And if you have any questions, I'd like to see a few proposed half reactions in the chat. And we'll discuss in about another 2 to 3 minutes. So again, we're trying to identify the oxidation and reduction half reactions. And then once we have that identified, we're going to show that this redox reaction is in fact balanced. Okay, so let's discuss this example. So first and foremost, we're going to assign oxidation numbers. So the oxidation number of aluminum is 0 in aluminum solid. In water, the oxidation number of oxygen is -2 and hydrogen is +1. The oxidation number of aluminum in aluminum hydroxide is +3. The oxidation number of oxygen is -2, hydrogen is +1. What is the oxidation number of hydrogen in hydrogen gas? Would someone like to share that in the chat or verbally? What is the oxidation number of hydrogen in hydrogen gas? What's the oxidation number of hydrogen in its pure element form? 0. Yep. That's exactly right. The oxidation number of a neutral pure element in its standard state is 0. Okay, so now that we have our oxidation numbers assigned, let's look first at aluminum. So we are going from 2 aluminum solid to 2 aluminum (3+). Okay. So we're going from an oxidation number of 0 to +3 So our difference is 3 minus 0, which is 3 electrons per aluminum atom. We have 2 aluminum atoms, so that gives us 6 electrons lost. And since we're losing electrons, this is an oxidation half-reaction. How do we get plus 3? Just like before, we can use our charge method. So if we reverse cross our subscripts, that gives us the theoretical charge, which is the same as the oxidation number for aluminum. Good question, good question. Okay, so continuing on with this idea, how do we know? You can use the cross method when your total charge is 0. If your total charge is not 0, you have to use another method. You have to use the equation method. So now looking at water, we have 3H2O, which will 3H2O going to 3H2. Let me just write this 3H2O as 6H plus going to 3H2. It's a little bit tricky in this case because our oxidizing agent is part of another molecule. So we have 6H plus going to 3H2. So the oxidation number of hydrogen in this case is +1 in H plus. For H2, it has an oxidation number of 0. So our delta is 0 minus 1, which is -1. So we have 1 electron gained per hydrogen atom. And if we multiply by 6, that gives us 6 electrons. And these are 6 electrons gained. Okay, so this is going to be our reduction half reaction. So when we add our equations together, so we have 2 aluminum solid plus 3H2O liquid leads to 2 aluminum hydroxide. We see that when we add our equations together, the number of electrons are identical on each side. You don't multiply by 6 until after you have the total number of electrons gained or lost per atom. You can multiply by 6 before if you want, but the key thing is the change in oxidation number, which is the electrons gained or lost by a single atom, is just based on the change in oxidation number for that single atom. Does that make sense? Perfect. So let's do another example. This time we are given a word equation. So we'll be doing an example where we deal with a word equation. So we're asked to write out a balanced chemical equation. And then once we have the balanced equation, I'd like you to identify the half reactions, the oxidation and reduction half reactions. And once you've identified the oxidation and reduction half reactions, I'd like you to show that electrons are conserved. So we'll spend about 3 minutes initially just writing out the chemical equation, and then we'll discuss once we have our balanced chemical equation. So let's spend about another 2 minutes to try to get a balanced chemical equation. And the response I see in the chat for the balanced chemical equation looks perfect so far. And don't be shy to submit your proposed response for the balanced chemical equation. And we'll discuss this example in about another minute to minute and a half. Okay, so let's discuss this example. So zinc, we write as zinc solid, sulfuric acid. So we have H plus and SO4 2 minus. So we cross the charges and we get H2SO4 aqueous. They're going to react to give hydrogen gas, which is H2, and zinc sulfate. So we have zinc 2 plus, SO4 2 minus. We cross the charges, and that gives us zinc sulfate aqueous. Now that we have our balanced chemical equation, I'd like you to take another 4 minutes and try and write out the oxidation numbers. I'd like you also to write out the change in oxidation number for each of our reactants, and then identify the oxidation and reduction half reaction. So don't be shy to message me with the proposed half reaction for either your oxidation or reduction half reaction. Then we'll discuss this example in about 4 minutes. Let's try to get a few more responses in for the balanced half reactions with the electron counting all set up. And we'll discuss this example in about another 2 to 3 minutes. Okay, so let's discuss this example. So assigning oxidation numbers, we went from zinc 0 to zinc 2 plus. Hydrogen, we went from +1 to 0. So looking at zinc initially, so we have zinc solid going to zinc 2 plus. So we went from an oxidation number of 0 to +2. So our difference is 2 minus 0, or 2 electrons per zinc atom. So times 1, that gives us 2 electrons lost. So this is an oxidation half-reaction. Next, looking at sulfuric acid, we have 2H plus aqueous leading to H2 gas. So looking at our difference in electrons, we went from +1 to 0. So we have 0 minus 1, which gives us 1 electron per hydrogen atom. And we have 2 hydrogen atoms. That gives us 2 electrons, and this is 2 electrons gained. So we've gained 2 electrons. So this is our reduction half-reaction. If we add together our oxidation and reduction half-reaction, we get the following result. As we can see, looking at our number of electrons are identical on both sides of the reaction equation. So they cancel, giving us zinc solid plus 2H plus leads to zinc 2 plus H2 gas. And this is our complete balanced equation. And you may notice that when you try balancing and combining half reactions, you end up with the net ionic equation in most cases. Does this make sense to everyone so far? Any questions on this example? Okay, so let's continue on now and let's talk a little bit about how do we balance redox reactions? How do we go about balancing redox reactions? So first we assign the skeletal net ionic equation. So we already have our net ionic equation up here. You're going to assign oxidation states to all atoms. We're going to assign oxidation states to all atoms. So looking at chromium, so let's do the easy ones first. Oxygen's -2, hydrogen's +1, chromium 3 plus is +3, oxygen's -2. Now let's do the difficult ones. So chromium and chromium oxide is equal to the oxidation number of oxygen times the number of oxygen atoms minus the total charge over the number of chromium atoms. And that in turn gives us an oxidation number of +6. Okay, now let's look at nitric acid, not nitric, but nitrous acid. So calculating the oxidation number of nitrogen, we have -2 times 2 plus 1 times 1 for the +1 oxidation number of hydrogen over 1. And that in turn gives us an oxidation number of +3. We're almost done. Just to have everyone help me out here, what is the oxidation number of nitrogen in nitrate? What is this oxidation number here? And let's try to share our responses in the chat. What is the oxidation number of nitrogen in nitrate? +5, yep. So to show the calculation for that, we have the oxidation number of oxygen times 3 oxygen atoms minus the total charge, which is -1, over the number of nitrogen atoms, which gives us +5. Exactly right. Okay, perfect. So now that we have the oxidation numbers assigned, we note any atoms that increase in oxidation state, and we write this for our oxidation half-reaction. So what atoms are increasing in oxidation state? What atoms are losing electrons? Is it nitrogen or chromium? What is losing electrons? What oxidation number is becoming more positive, larger? Nitrogen, yep. So we write all chemical species associated with nitrogen where we are losing electrons, going up in oxidation number. Okay. We're going to repeat the same process where we write any atoms that decrease in oxidation state and gain electrons. So chromium is gaining electrons, right? If one species is losing electrons, the other one must be gaining in order for electrons to be conserved. Okay, so with that established, let's just write out chromium. So we have Cr2O7 2-, leading to chromium 3+. So we went from +6 to +3. Don't worry, these are just the rough skeletal outlines that we're going to take forward in the balancing process. Okay, so now that we have our equation set up, what we're going to do is we're going to write the number of electrons gained or lost by each species. If it loses electrons, electrons are on the product side. This should be for your oxidation half-reaction. If we gain electrons, the electrons go on the reactant side, which is our reduction half-reaction. So looking at the first case, looking at our oxidation half-reaction, how many electrons did we lose? How many electrons did we lose? In total, how many electrons did our nitrogen atoms lose? If we went from +3 to 5, 5 minus 3 gives us, what's 5 minus 3? 2, yep. So we have 2 electrons per nitrogen atom. We have 1 nitrogen atom. So that gives us 2 electrons lost. So in chromium oxide in dichromate going to chromium 3, one thing that you have to be really careful of is you need to make sure that your atoms are balanced. Do we have the same number of chromium atoms on each side? Do we have the same number of chromium atoms on each side? Yes or no? Do we have the same number of chromium atoms on each side? No. So we need a coefficient of 2. This coefficient of 2 will be important. So now checking, we went from +6 to +3. So our difference is equal to 3 minus 6. So we have 3 electrons per chromium atom. So how many total electrons did we pick up if we have 2 chromium atoms? How many total electrons were gained by dichromate? How many total electrons were gained by dichromate? So that's 3 per chromium atom, but since we have 2 chromium atoms, we have 6 electrons total. That is why I always had you make a note and always double check that your main atom is balanced when you're counting electrons. Does this make sense? Any questions on this idea? Okay, so now that we have our rough oxidation and reduction half reactions, so for example, we are going to make sure to balance all atoms except for hydrogen and oxygen. So for our nitrous acid going to nitrate, went from +3 to +5. We've lost 2 electrons. Are all of our atoms except for hydrogen and oxygen balanced in this half reaction? Are all atoms except for hydrogen and oxygen balanced in this half reaction? Do we have the same number of atoms on each side except for hydrogen and oxygen? Yeah, it looks good as a first pass. Okay, now looking at dichromate. So we have Cr2O7 2-, leading to 2 chromium 3+ plus 6 electrons. Are all of our non-hydrogen, non-oxygen atoms balanced for this reaction? Yes, okay, perfect. So now what we have to do is we have to balance the hydrogen and oxygen atoms. So under acidic conditions, you balance oxygen atoms by adding water. Then you balance hydrogen atoms by adding hydrogen ions. So let's try this out. So let's rewrite our let me just check really quickly. Oh, that should be NO3-. So let's rewrite our equation. So this is our oxidation half-reaction. So following the logic associated for redox reactions, and this is very different than normal chemical equation balancing in that for redox reactions, you can add molecules of water or H+ to either side of your equation to balance hydrogen and oxygen. This is the only example in balancing where you can add chemical species to each side of your chemical reaction to generate a balanced equation. So if we have 2 oxygens on the left and we have 1 oxygen on the right, my question to all of you is, for our oxidation half reaction, how many molecules of water do I need to add? 2 plus, how many molecules of water do I need to add, and to what side? So if I have 2 on the left and 1 on the right, 1 plus what would give us 2 oxygens? How many waters do I need to add? Oh, sorry, let me just reset that. I'm thinking of I got one step ahead. I'm thinking of hydrogen. So we have 2 oxygens on the left, we have 3 oxygens on the right. So 2 plus what would give us 3? So we'd need 1 water on the left. So now we have equal numbers of oxygens on each side, but now we have 3 hydrogens on the right and 0 hydrogens on the left. Sorry, 3 hydrogens on the left and 0 hydrogens on the right. So now we have to add H+. And what times 1 would give us 3 hydrogens? How many H pluses do we need to add? 3. Okay, so just to recap what we did, we counted the number of oxygen atoms. We noticed there were 2 oxygen atoms on the left, 3 on the right. We needed 1 more oxygen atom on the left, so we added a water molecule to the left. Then we counted hydrogen. We noticed we had 3 hydrogens total on the left, 0 on the right, so we added 3 H+. So this equation here is now balanced with respect to atoms. So this is our complete oxidation half reaction. Let's look at our reduction half reaction. Let's look at the reduction half reaction under acidic conditions. So if we have Cr2O7, 2 minus, leads to 2 chromium 3 plus 6 electrons. Let me give a little more space. I'm going to write this with a little more space just so that way when we add all of our chemical species to each side, we don't run out of space. Okay, so now that we have this equation set up, let's do a count for oxygen atoms. We have 7 oxygens on the left. We need 7 oxygens on the right, so we'll add water. And what times 1 will give us 7 oxygens? How many waters do I need to add to the right? How many waters do I need to add to the right? 7. Okay, so that also gives us 7 times 2, which is 14 hydrogens. So now we have to balance hydrogen. So to balance hydrogen, we need to add how many H plus? 1 times what would give us 14 H plus? How many H pluses do I need to add? 14. So we have 14 H plus. Okay, perfect. So now we have our balanced oxidation and reduction half reaction. Okay, so this is what it would look like under acidic conditions. You can use water and H plus. So this is under acidic conditions. Now let's talk about everyone's least favorite conditions, which are basic conditions. And under basic conditions, you balance oxygen atoms by adding hydroxide ions, then, and only then, you balance hydrogen atoms by adding water. Now, students often get a little confused when they're balancing under basic conditions. So I have the following cheat sheet in terms of what to add to each side of your equation if you want to add a certain number of oxygen or hydrogen atoms to either side. I would be familiar with how this works, as this is a pretty powerful shortcut if you want to quickly adjust the number of oxygen or hydrogen atoms under basic conditions. So let's do an example. So suppose we're looking at our nitrous acid reaction going to nitrate. Okay. So now looking at this equation, we have 2 oxygens and 1 hydrogen on the left, and I have 3 oxygens on the right. So then, first and foremost, I need, just in terms of what I need, for basic conditions, I like to make like a little bit of a need table. So I need +1 oxygen on the right-hand side. Okay. And I also need +1 hydrogen on the left-hand side. Okay, so looking at my reference sheet, if I wanted to add 1 oxygen atom to the right, I add the following pair. So I'd add H2O leads to 2OH. And if I want to add 1 hydrogen to the left, I add H2O leads to OH minus. So now that I have both of my oxygen and hydrogen addition units set up, I just simply add them to my overall chemical equation. So that in turn gives us, after adding our equations together, we get HNO2 plus 2H2O leads to NO3 minus plus 3OH minus. Oh, so just to check one more thing. when balancing this equation, we'd need one hydrogen on the right-hand side, and we need one oxygen on the left. So I had this completely reversed. So to add one oxygen to the left, we need to have 2 OH minus leads to H2O. If we want to add one hydrogen to the right, we go OH minus leads to H2O. So now we add each of those units to our chemical equation, and then we check to verify that the chemical equation is balanced. Always make sure you're checking your work. It allows you to detect errors, and it allows you to avoid ending up with an unbalanced equation. So now checking just to make sure that this equation is in fact balanced. I have 4 hydrogens on the left, 4 hydrogens on the right, and I have 5 oxygens on the left, 5 oxygens on the right. So this equation is now balanced under basic conditions. Does that make sense to everyone so far? So that's one of the methods of balancing under basic conditions. We add these equation units that either add oxygen or hydrogen to the left or right. And once we've added the appropriate number of oxygens or hydrogens to each side, then we add our equations together and check that the equation's balanced. Let's do another example. So Cr2O7 2- leads to 2 chromium 3+. So we have 7 oxygens on the left. So in terms of what we need, we need plus 7 oxygens to the right-hand side. Okay? So then we'd add the following unit 7 times because we need 7 oxygens. So we'd have H2O leads to 2 OH minus. So let's add 7 H2O leads to 14 OH minus. And if we add our equation together, we have Cr2O7 2- plus 7 H2O leads to 2 chromium 3+ plus 14 OH minus. So this is our reduction half reaction under basic conditions. Does this idea make sense to everyone? Any questions on balancing redox reactions under basic conditions? Can I get some responses in the chat if anyone has any questions, if it makes sense to everyone? It will tell you whether to balance under acidic or basic conditions. I'm just right now showing you how to balance under both of those conditions, but you'll be told in these problems whether it needs to be balanced under acidic or basic conditions. So as an alternative, under basic conditions, there's a nice trick. If you really like balancing equations under acidic conditions, you can balance the basic equation as though it were under acidic conditions. So for example, looking at the following equation, I have 1 oxygen on the left. I need to add 1 oxygen to the right. So I add my water. Now I have 1 oxygen and 2 hydrogens on the right. So now I add my 2H+, and now I have a balanced equation under acidic conditions. But if the problem's asking for basic conditions, you may say, well, I guess I'm stuck. Well, not really. What you do is you write out your equation under basic conditions. And then what you do is you very carefully count the number of H+ ions that you have. and then you add hydroxide to each side equal to the number of H+ ions. So how many hydroxides do I need to add to each side? How many hydroxides do I add to each side? 2, okay? And we know that H+ plus OH minus will create water. So this will end up generating 2 water molecules. So we write out our equation. So 2H2O liquid plus ClO minus aqueous leads to Cl minus plus H2O plus 2OH minus, and then we cancel water molecules on each side. We have 1 on each side, so we cancel 1 water molecule. That gives us the following balanced equation under basic conditions. Does that idea make sense to everyone? Is everyone comfortable with this idea? Does this seem a little easier than the normal basic method?
What do you get the 2 OHs?
We add 2 hydroxides to each side because you add hydroxide to each side equal to the number of H+. Because our goal is to convert all of our H+ into water, and so we only have OH minus and water. So when you think basic conditions, I want you to think hydroxide. Does that make sense? So we add 2 OH to each side because we have 2 H+ that we want to get rid of. Did that address your question?
Yes, thank you.
Perfect. So let's try this out. Let's try this out. Let's try this out on our previously generated acidic reaction conditions. So let's try and convert our oxidation reaction that we have under acidic condition into basic conditions. So we have HNO2 leads to NO3 minus plus 3H plus. Just checking from before. One moment, just checking our, yep. Okay, so that's our previously drawn acidic conditions. Now, if we wanted to convert this acidic half reaction into basic conditions, what do I add to each side? How many hydroxides do I need to add to each side? How many hydroxides do I need to add to each side? 3, yep, because we have 3H+, so I add 3 hydroxides to each side. That gives us 3 hydroxide plus water plus HNO2 leads to NO3 minus plus, and remember H+ and OH combine to make water, which gives us 3H2O. And if we cancel out our water molecules, that in turn gives us 3 OH minus plus HNO2 leads to NO3 minus plus 2 H2O, which is exactly what we got when we tried balancing this equation under basic conditions. Does that make sense to everyone? So we went from acidic to basic conditions, and we can readily modify our half reaction from an acidic half reaction to a basic half reaction. Does that make sense to everyone? Does this idea make sense? Is everyone feeling comfortable with the mechanics behind balancing these equations? So let's practice the last step, and this is why you need to know how to count your electrons. So for the last step, you're going to multiply each half reaction by an appropriate whole number so that the number of electrons in each half reaction are equal. You're generally looking for the least common multiple. So let's do a few examples. So if we have 3 electrons lost on the top and we have 2 electrons gained on the bottom, what is our least common multiple? What is our least common multiple number of electrons? What's the smallest common multiple between 3 electrons and 2 electrons? 6. So we're going to multiply the top equation by 2, the bottom equation by 3. Okay, perfect. Now let's look at this equation here. So we have 2 electrons lost in the top. We have 5 electrons gained. We have 5 electrons gained on the bottom. What is the least common multiple between 2 and 5?
10.
10. Yep. So we're going to multiply the top equation by 5 and the bottom equation by 2. So let's show an example using the chemical equations that we've generated previously. So we've been carrying through this example of nitrous acid going to nitric acid and losing 2 electrons, reacting with chromium or dichromate, which is Cr2O7 2- plus 14H plus, leading to 2 chromium 3 plus 7H2O. And again, we've gained 6 electrons in this bottom example. Okay, so what is the smallest common number between 6 and 12? And in this case, you may not need to use the least common multiple. You just want to find the smallest common number of electrons between these 2 equations. And what's the smallest common number between 2 and 6? What's the smallest common number between 2 and 6? If I want these 2 equations to have the same number of electrons, what should I multiply my top equation by?
2.
What was that?
2.
Multiply the top equation by 2. If I have 2 electrons on the top and 6 on the bottom, what is a common number between 2 and 6?
3.
Yep. So 2 and 6, the smallest common number would be 6 electrons. So if our goal is to have 6 electrons in each of our equation, we're going to multiply our top equation by 3. So separating out our coefficients, that gives us, I'm just going to draw a little dividing line here. That gives us 3H2O plus 3HNO2 aqueous leads to 3 NO3 minus plus 9H plus 6 electrons. We have equal numbers of electrons on each side. And now we're ready for the last step, which is the easiest step, where you add the 2 balanced half reactions together and you cancel out species that appear on both sides. So if we have 14H plus Cr2O7 2- leads to 2 chromium 3 plus 7H2O, and we're combining that with 3H2O plus 3HNO2 leads to 3 NO3- plus 9H plus 6 electrons. Our electrons should cancel. If the electrons don't cancel, you need to go back to an earlier part of the problem. Then we're going to cancel water. We have 3 on each side, so we're going to cancel 3 waters from each side. 7 minus 3 is 4. We're going to cancel 9H plus from each side. 14 minus 9 is 5. And that gives us the following equation. We have 5H plus Cr2O7 2- plus 3HNO2 leads to 2 chromium 3 plus 3 NO3- plus 4 H2O. And now that's our complete balanced redox reaction. Now for step 12, check to make sure your reaction is balanced. This is under acidic conditions. So we have a total of 8 hydrogens, 2 chromiums, and 13 oxygens on the left. We have 2 chromiums. Oh, and we also have 3 nitrogens. We have 2 chromiums, 3 nitrogens, 13 oxygens, and 8 hydrogens on the right. So this equation is balanced. Don't forget the last step. Many times I see that students make a small error in one of these steps for your redox reaction. They get to the end and they don't check that their equation is balanced. You have all the tools at your disposal to check that an equation is balanced, and it will definitely tell you if something is correct or incorrect in your balancing process. So this is one complete example worked from start to finish. Let's do another example so that we're 100% confident on how to balance redox reactions. Any questions on balancing redox reactions? I know it's very steppy and it's very different than most balancing of normal chemical reactions, but I find once you understand the procedure and you practice it a few times, it becomes a very quick and efficient way for balancing redox equations, even as an alternative to normal balancing methods for redox reactions. Any questions? Any questions I can address? Okay, so let's look at the following example and let's try to balance the following redox reaction. So this one's pretty easy. We're not integrating the acidic or basic condition stipulations yet. Just balance the following redox reaction. And I'd like you to write net ionic equations for each reaction and write the oxidation and reduction half reactions. So this is an equation that you can balance using the normal method, but I'd like you to try to balance this equation using the redox method. So that way you're getting familiar with utilizing the redox method of balancing. And we'll discuss this example in about 3 to 4 minutes. And don't be shy to message me with your proposed balanced chemical equation. And don't be shy to message me with your proposed balanced equation or coefficient for the following redox reaction. And we'll discuss in about another 2 to 3 minutes. And the balanced equations that I'm seeing in the chat look good so far. Let's try to get a few more responses and we'll discuss in another minute and a half. Okay, so let's look at this example. So we have bromine. So let's first assign oxidation numbers. So bromine is 0, sodium is +1, iodine is -1, bromide is -1, iodine is 0. Perfect. We now have our oxidation numbers established. Let's write our oxidation half-reaction, the species that is becoming more positive or increasing in oxidation number. So we have sodium iodide. I'm going to get rid of the sodium. So we have iodide going to iodine. Now, first and foremost, before we even start counting electrons, we need to balance this equation. Is this equation balanced in terms of non-hydrogen, non-oxygen atoms? Is this equation balanced in terms of non-hydrogen, non-oxygen atoms? Is this equation balanced? No. We have two iodines on the left. We have one iodine, sorry, we have two iodines on the right. We have one iodine on the left. And 1 times what would give us 2 iodines? 1 times what would give us 2? 2, yep, exactly right. So we have 2I minus leads to I2. Now counting electrons, we have our difference in electrons is equal to 0 minus -1. So that's a difference of 1 electron per iodine atom. We have 2 iodine atoms. So that gives us 2 electrons total lost. Now, continuing on from that, we're going to look at bromine. So we went from Br2 liquid to Br minus aqueous. And before we do anything, is this equation balanced? Is this equation balanced with respect to non-hydrogen, non-oxygen atoms? Is this equation balanced? No, we have an oxidation number of 0, -1. We have 1 bromine on the right. We have 2 bromines on the left. 1 times 2 would give us 2 bromines. So now that we have that established, we can calculate the number of electrons gained. So our difference in this case is -1 minus 0. So then we have 1 electron per bromine atom. We have 2 bromine atoms, so that gives us 2 electrons. As our oxidation number is becoming more negative, we are gaining electrons. So we would call this reaction the reduction half reaction. So now if we want to combine our oxidation and reduction equations together, so we have 2I minus aqueous leads to I2 plus 2 electrons. We have 2 electrons plus bromine liquid leads to 2 Br minus aqueous. Our electrons are the same, so we can add our equations together. And that in turn gives us our net ionic equation of 2I minus aqueous plus Br2 liquid leads to I2 solid plus 2Br minus aqueous. So here's our complete and balanced net ionic equation. Does this example make sense to everyone? Is there any questions on this example? Any questions on this example? Okay, so let's keep going now and let's work on a little more complicated examples. So let's take a look at the following redox reaction. And I'd like you to attempt to balance the following redox reaction, writing half reactions, and then write a net ionic equation for the overall reaction. So we'll spend about 4 to 5 minutes working through this problem, and I'd like to see some balanced redox equations in the chat. And we'll discuss this example in about 4 to 5 minutes. And if you have any questions working through when you're balancing these equations, again, don't be shy to type your questions in the chat or unmute and ask your questions verbally. It does take a fair amount of practice to get comfortable with these redox reactions, but we'll work through it together as a class. And we'll discuss this example in about another 2 to 3 minutes. And I'd like to see a few proposed balanced equation in the chat. And I would double check the coefficients for this reaction. As this is a redox reaction, you have to make sure that the number of electrons is balanced, not just the number of atoms. And we'll discuss this example in about another minute. And just remember, make sure that your number of electrons are balanced in both of your half reactions. Okay, so let's discuss this example. So first and foremost, we need to assign oxidation numbers. So aluminum is 0, aluminum 3 plus is +3, hydrogen is +1 in HCl, chloride is -1, hydrogen and hydrogen gas is 0. So now that we have that set up, now what we're going to do is we're going to write out our oxidation and reduction half reactions. So we have aluminum going to aluminum 3 plus aqueous. So as we went from 0 to +3, our difference is 3 minus 0, or 3 electrons per aluminum times 1 aluminum atom. So we have 3 electrons. And now based on this change in oxidation number, did aluminum gain or lose electrons? Did aluminum gain or lose electrons? It lost electrons, right? Okay, next, let's look at hydrochloric acid. So I'm going to separate out the chloride because this is a strong acid. So you're going to have H plus aqueous leads to H2 gas. And we went from an oxidation number of +1 to 0. Now, before we do anything, we need to balance this equation. Before we do anything, we need to balance this equation. We have 2 hydrogens on the right. We have 1 hydrogen on the left. So what coefficient do we need for H plus? What coefficient do we need for H plus? How many hydrogens do we need on the left? 2, exactly right. So now we have 2H plus leads to H2. So then our difference in electrons is 0 minus 1. So we have 1 electron per hydrogen atom. We have 2 hydrogen atoms. That gives us 2 electrons. And did we gain or lose 2 electrons? Did we gain or lose 2 electrons? Did we gain or lose 2 electrons? Did H plus gain or lose electrons?
Gain.
Gain, yep, it gained 2 electrons. So now we can combine our oxidation and reduction half reactions. And in order to do that, what we're going to need to do is we're going to need to find the common multiple, or the common number of electrons, in order for our total number of electrons on each side to cancel. So then, if we have 3 electrons on our top equation and 2 electrons on our bottom equation, what is our common number of electrons between both of our reactions? What is the common number of electrons between both of our reactions? What is the common number of electrons between 3 and 2?
6.
Yep, exactly. So we're going to multiply the top equation by 2, the bottom equation by 3. So executing on that, we have 2 aluminum solid leads to 2 aluminum 3 plus 6 electrons. And then we have 6 electrons plus 6H plus aqueous leads to 3H2. Our number of electrons are the same. So when we add this equation together, we get 2 aluminum solid plus 6H plus aqueous leads to 2 aluminum 3 plus aqueous plus 3H2 gas. And here we go. That's our balanced chemical equation. Notice a key feature is that redox reactions have to be balanced with respect to electrons. They cannot just be balanced with respect to atoms. Does this help everyone? Does this help make really clear the main difference between redox reaction balancing and normal chemical equation balancing? Redox reactions, you have to pay special attention to the number of electrons gained or lost. Does that make sense? Can I get some responses in the class that are in the chat that everyone's comfortable with this idea? Or if you have any questions or any questions I can address?
So you balanced it based on the electrons,
Yes.
but you couldn't have just canceled out like 2 from the bottom one and then had plus 1 electron on the top?
Not in that case, because there'd be no way to cancel that remaining electron without adjusting the coefficients of your equation.
Oh, okay, because you don't want it in your final solution.
So chemical equations have to be balanced with respect to atoms and with respect to electrons. And this least common multiple method ensures that all of your atoms stay balanced while you adjust your coefficients to balance the number of electrons.
Oh, okay, that makes sense.
That makes sense?
Mm-hmm.
Perfect. So let's try a little bit more of a difficult example. This is something that you may see on an exam or a quiz. This is the type of redox reaction at the most difficult that you'd be expected to balance. So I'd like you to look at the following equation. I'd like you to assign oxidation numbers and then try to balance this equation under acidic conditions. And we'll give everyone about a total of 7 minutes on this problem. And in 3 minutes, we're gonna look at the half reaction involving oxalic acid. So I'd like you to start with oxalic acid and then move on to permanganate. And we'll get both the half reactions written and we'll start looking over in about 3 to 4 minutes our first half reaction. And don't be shy to message me with your proposed balance chemical equation in the chat. And if you have any questions, don't be shy to ask. And we'll discuss in about another 3 minutes. And I'd like to see a few proposed half reactions or balanced equations in the chat. And we'll talk about the first half reaction in about another 2 to 3 minutes. And if you have any questions, don't be shy to ask them in the chat or verbally. And as you work through this problem, if you need a little bit more time, can I get some responses in the chat if you'd like a little bit more time on writing out the first half reaction? How's everyone doing on the first half reaction? Can I just get a sense of it in the chat? Okay. I'll give everyone a little bit more time for the first half reaction, and we'll discuss in about another 2 to 3 minutes. Okay, so to give everyone a little bit of guidance, let's look at this first half reaction involving oxalic acid. So we have H2C2O4 going to carbon dioxide. Okay, now looking at our oxidation numbers, in carbon dioxide we have an oxidation number of +4. In oxalic acid, our carbon oxidation number is -2 times 4 plus 1 times 2 over 2, which gives us an oxidation number of +3. Now, before we even think about counting the total number of electrons, we have 2 carbons on the left, we have 1 carbon on the right, and 1 times 2 would give us 2 carbons. Okay, so now looking at our difference in the number of electrons, we have +4 minus 3, which gives us 1 electron per carbon atom times 2 carbon atoms. So that gives us 2 electrons lost. Perfect. So now that we have our electrons balanced, we have to look at this equation one more time, and we see that we have 2 hydrogens on the left and 0 hydrogens on the right. So how many H plus do I need to add in order to get 2 hydrogens on each side? How many H plus do I need to add in order to get 2 hydrogens on each side? Oh, sorry. What times 1 would give us 2 hydrogens? We'd need 2 H plus. So this is our first balanced half reaction. I'd like you to take another 4 minutes and try to write the second half reaction balanced under acidic conditions. And we'll discuss the second half reaction in another 4 to 5 minutes. Oh, and we see someone writing a proposed half reaction per permanganate already. And I see in the chat as well that the electron counting looks good. But let's try to balance as well our number of hydrogen and oxygen atoms. But the electron counting that I see in the chat and the precursor equation that I'm starting to see using the annotate feature looks good so far. And don't be shy if you have any questions or ideas. Don't be shy to write your proposed balanced equation in the chat. Or if you have a question, don't be shy to unmute and ask your question in the chat or verbally. I'm sure if you have a question, other students may also have the question as well. So one thing to keep in mind is that the oxidation number for the metal will be positive as you're using an absolute value, and your total charge is -1. So you need to subtract -1 from your oxidation number total. So your oxidation number would be +7 instead of 8. And looking in the chat, I see a reasonable half reaction for this reaction. Let's keep working through this example. It's always good to get a sense of how students are progressing through these problem-solving sessions. And we'll discuss in about another 2 minutes, just to give everyone some more time. So now that we have the first portion of this half reaction balanced via the annotate feature, and we have our electrons counted, let's now balance the hydrogen and oxygen atoms under acidic conditions. And remember, when you think acidic, you should think H+ and water. And we'll discuss balancing the second half reaction in a few minutes. Yep, the number of water molecules looks perfect. Yep. So the balanced equation that I see via the annotate feature looks great. So let's discuss our second half reaction. So we looked at the oxidation half reaction. Now let's look at the reduction half reaction. So we have permanganate going to manganese 2+. So for manganese, the oxidation number of manganese is the oxidation number of oxygen times the number of oxygen atoms minus the total charge under the number of manganese atoms. That gives us +7. Manganese 2+ is +2. All of our atoms are balanced besides oxygen and hydrogen. So our difference in the number of electrons is 2 minus 7. So we have 5 electrons gained per manganese atom times 1 manganese atom. And that in turn gives us 5 electrons total. So we've gained 5 electrons. Now looking at this equation, we have 4 oxygens on the left. So in turn, we need 4 oxygens on the right. So we'll add 4 water molecules. Now we have 8 hydrogens on the right. So in turn, we add 8H+ to the left. And that gives us the following balanced redox half reaction. So now the last step, finishing off this problem, we can do that together. So we write out both of our half reactions. We write out both of our half reactions. And now what we do is we find the least common multiple between our two half reactions. So what is the smallest common number of shared electrons? What is the smallest? 10. Yep. Perfect. Okay, so now that we have our smallest number of shared electron count established, now that we have that count established, what we're going to do is we're going to multiply the top equation by 2 and the bottom equation by 5 to get 10 electrons each. And then what we're going to do is we're going to add our equations together. As you see, these redox reactions take a few steps. So we have 16H plus 10 electrons plus 2 MnO4 minus leads to 2 Mn2 plus 8 H2O. Then we have 5 H2C2O4 leads to 2 CO2 plus 10 H plus 10 electrons. The electrons cancel. We cancel 10 hydrogens on each side, and we're left with, as our final reaction, 6H plus 5 H2C2O4 leads to, oh, this should be a 10. Plus 2 MnO4 leads to 10 CO2 plus 2 manganese 2 plus 8 H2O. So here's our final balanced redox reaction. Yep, and I just want you to check now really quickly. Is this equation balanced with respect to atoms? At the end of the day, your redox equation should be balanced with respect to electrons and with respect to atoms. So I'd like you just to take a moment and check, is this equation balanced with respect to atoms? Yes or no? Did we do a good job here? Did we get everything aligned correctly? Yes, so let's put a check mark. Perfect. Always do that last step. It doesn't take a lot of time, but it can save you a lot of lost points. So this was some additional space. And now, although it seems like I'm asking you the same question, I'd like you to try and balance the following redox reaction, which is the exact same one that we discussed in the earlier example, except this time I want you to balance it under basic conditions. And I'm just going to let you look at the two half reactions that we made. I'd like you to take about 4 to 5 minutes, and I'd like you to convert these half reactions and chemical reactions developed under acidic conditions into basic conditions. And don't be shy to message your proposed or write out your proposed basic redox reactions. I'm just going to scroll down if someone wants to use the annotate feature just to give everyone some space. And you're more than welcome to share your responses in the chat or using the annotate feature. And we'll discuss this basic balancing problem or balancing under basic conditions in about another 3 to 4 minutes. But I'd like to see a few responses in the chat just to make sure we're all on the same page. And one hint is you don't have to start from scratch. If we've already done a great job of writing out a balanced acidic half reaction, all you have to do is take your acidic half reaction and convert it into basic conditions. So looking at the following half reaction, the half reaction written using the annotate feature from scratch under basic conditions looks perfect. Let's try to get our second half reaction written down. And as we have the first half reaction pinned down, let me show you how to write out the half reaction under basic conditions. If you are trying and you already have the acidic half reaction. So let's suppose we have this acidic half reaction just sitting around ready to use. Now you could generate it from scratch. That method that was proposed by a student is perfectly 100% correct. But if we already spent all this time and effort, let's just convert all of our H plus into water by adding 2 hydroxide to each side. That in turn gives us H2C2O4 aqueous plus 2 OH minus leads to 2 CO2. Remember, H plus and OH combine to make water, plus 2 H2O plus 2 electrons. And from that, we've saved ourselves a fair bit of time. So whenever you're asked to deal with balancing redox reactions under acidic and then basic conditions, make sure you save your work for your previous half reactions, because you can easily convert an acidic half reaction to a basic half reaction. So here's our first half reaction. I'd like you to take another 2 to 3 minutes and try to write out the second half reaction under basic conditions. And don't be shy to submit your proposed responses in the chat. Oh, would you be able to write it a little bit more to the left? But it looks great so far. It was just going off screen, but I'd actually like to see the proposed response using the annotate feature or in the chat, just so that way I know that we're progressing through and we're comfortable with each step of this problem solving session. You're on the right track there. You're on the right track there. Yep, looks good. Yep, looks reasonable. Let me just check really quickly. Yep, looks perfect. So let's talk about this example. I'm just gonna clear the annotate. So it's really nice to see what methods the students prefer to use. That was the from scratch method. I'll show you the method from modifying the acidic half reaction. So we have 8H plus MnO4 minus plus 5 electrons leads to Mn manganese 2 plus 4H2O. Okay, and now as a trick, what we can do is we can just add hydroxide to each side equal to the number of H plus. Whoops, one moment, sorry about that. OneNote got overloaded. 1 second. Okay, so my question to all of you is, so looking at our chemical equation, my question to all of you is, how many hydroxides do I need to add to each side? How many hydroxides do I need to add to each side to get rid of my H plus? How many hydroxides do I need to add? 8, yep. Okay, so that gives us 8 water molecules. We have 8 H2O plus MnO4 minus plus 5 electrons leads to manganese 2 plus 4 H2O plus 8 OH minus, and we can cancel 4 waters from each side. And that now gives us the following chemical equation. We have 4H2O plus MnO4 minus plus 5 electrons leads to manganese 2 plus 8 OH minus. Now let's write our other half reaction. We have H2C2O4 plus 2 OH minus leads to, oops, one moment, let me just refocus the camera. Leads to 2 CO2 plus 2 H2O plus 2 electrons. And again, just like before, we are doing the same pattern where we take a look at our chemical equation, we look at our number of electrons in each of our half reactions, and then we decide what whole number do I need to multiply both of my equations by. So let's start with the top. What should I multiply my top equation by so that my number of electrons on each side are equal? What should I multiply the top equation by? 2, yep. And the bottom equation we multiply by 5. So that in turn gives us 8H2O plus 2 MnO4 plus 10 electrons leads to 2 manganese 2 plus 16 OH minus. And then we have 5 H2C2O4 plus 10 OH minus leads to 10 CO2 plus 10 H2O plus 10 electrons. And this is really important. You have to convert each of your half reactions individually and then you combine them together. You can't take the end result and convert it from acidic to basic conditions. Okay, so now that we have 10 electrons on each side, We can cancel our electrons. We can cancel 10 hydroxides, and we can cancel 8 waters. And that gives us 5 H2C2O4 plus 2 MnO4 minus leads to 2 manganese 2 plus 10 CO2 plus 6 OH minus plus 2 H2O. So here's our following balanced equation under basic conditions. Is everyone feeling a little bit more confident with handling these redox balancing problems? I know it's a lot of steps, but it's important that you're familiar with balancing redox reactions because you'll see them a lot in general chemistry too. Any questions on this example? Really don't hesitate to ask. From what I've seen in the chat and from the annotate features, everyone seems reasonably confident with each of the individual steps. It's all about putting it together. Okay, so let's try to tackle a problem where we're balancing a redox reaction under basic conditions. So starting from scratch, let's do another redox balancing problem. I really want to make sure we're practicing this skill until we're completely comfortable with it. You'll see at least 1 to 2 redox balancing questions on your exam 3 and final. So you want to make sure you're comfortable with this topic. So let's give our best attempt to balance these redox reactions, and in about 4 minutes, we'll discuss the half reaction involving cadmium. This example, it's a little bit more straightforward in terms of the compound's complexity, but you need to be very, very careful with counting your atoms for this reaction. And make sure you're checking your oxidation numbers very carefully here. Redox reactions are balanced based on electrons, not just atoms. And we'll discuss in about 4 minutes. And looking in the chat, the electron counting looks, is that -2? I guess that's one way of thinking about it. Yes, the cadmium does lose electrons, but in terms of chemical equations, make sure to put the electrons lost on the product side and electrons gained on the reactant side. Just because for chemical equations, writing like a minus sign, it doesn't have necessarily the same physical meaning as in algebra. But the logic looks fine. And looking at the equation that is provided in the chat, yep, exactly right. So in the chat, the equation that was just provided looks perfect. Looking at the annotate feature response provided by one of our students, so looking at it, without that additional hydroxide, let me just count really quickly. So may I suggest, let's take a look at, so let's keep this up for right now, and let's just first and foremost just think, we have how many hydroxides on the right? How many hydroxides do I have on the right? 2, yep. So then how many hydroxides do I need to add to the left? 2, yep, perfect. So let's clear this and let's compile our class data together. Oh, whoops, sorry about that. But it's really good so far. I know basic conditions are really tricky to balance sometimes, but if we have cadmium solid leads to cadmium hydroxide, we can still use the logic of balancing based on ions. So we have 2 hydroxide on the right, so we're just going to add 2 hydroxide to the left. Okay, now let's do some electron counting. Cadmium solid has an oxidation number of 0. Cadmium hydroxide has an oxidation number of +2. Okay, so now that we have that established, how many electrons did we lose? What is our delta? 2 minus 0 gives us 2 electrons lost. So this is our oxidation half-reaction. Now, let's take a look and let's focus next on the nickel half-reaction. So let's take about another 4 to 5 minutes and try to write a valid half-reaction for the reaction of nickel 3 oxide.
Could you explain how you got the +2 on the cadmium hydroxyl?
Yes. So looking at the charge method, so we have cadmium hydroxide. So if we reverse cross our charges, that gives us cadmium +2. So the charge of cadmium is the same as its oxidation number. Does that make sense?
So you don't pay attention to the hydroxide? You're just looking at cadmium?
Yes. So in general, and we'll actually see this in this full equation, and this is a really good point. Hydrogen is +1, oxygen's -2, and in hydroxide, hydrogen's +1 and oxygen's -2. So hydroxide doesn't change in oxidation number. It's just there to make sure that the atoms are balanced and to properly reflect the fact that atoms are conserved. Does that make sense?
Okay, yeah, that's making more sense.
So in most cases, hydroxide and water are not going to change in oxidation number. I can't say every case because there are exceptions, but in most cases, hydroxide is just a placeholder that is there to balance our atoms in a redox neutral fashion. I noticed in the chat, someone had a question about the electrons. The best way that I like to go about it is I like to look at my oxidation numbers in my reactant and product. I subtract my reactant, I take my product oxidation number and I subtract my reactant oxidation number from it. If the number is positive, that means we have lost electrons. If it's negative, That means we've gained electrons. You then take your number of electrons gained or lost per atom, and you multiply it by the number of atoms, in this case 1 cadmium, to give us the total number of electrons. Does that make sense? If the oxidation number is going up, we're losing. If it's going down towards a negative number, we're gaining. Did that answer your question? Is there a part that I can elaborate on? So the electrons, if the number is positive and we're losing electrons, the electrons are on the product side. So lost electrons are on the product side and gained electrons are on the reactant side. Does that help? So if we're losing electrons, we're producing electrons, and electrons are on the product side. If we're gaining electrons, the electrons are on the reactant side. Does that make sense? No problem, no problem. Let's try to focus on and let's try to write our second half reaction, and let's try to apply what we've learned in this example to the nickel 3 oxide half reaction. And we'll discuss that portion of this example in about another 4 to 5 minutes. The initial oxidation number of assignments look good so far. Let's keep going through and assigning the remainder of the oxidation numbers. Perfect. Yep. The oxidation number assignment looks good. One thing that I'd like you to note is that you've calculated the electrons. Now, my question to you is, did we gain or lose electrons? You are correct that one electron was transferred, but did we gain or lose electrons? Did we gain or lose electrons? Now, to follow up on this, that's one electron gained per nickel atom. And now my question to you is, how many nickel atoms are participating in this reaction? And as a hint, you may want to balance this reaction. There we go. So how many nickel atoms are transferring that one electron? How many total electrons do we transfer across both of our nickel atoms? 2. There we go. So where do we put our electrons? On the left or the right-hand side? Where do we put our electrons? On the left or the right-hand side? Perfect. Perfect. Exactly right. Exactly right. Okay. Wonderful. So we have a rough sketch of this equation, and I'd like the class to help pitch in and share some of their ideas. How would we balance this equation with respect to hydrogen and oxygen atoms? This skeleton with the electron count is perfect. We just need to finish it off and balance the hydrogen and oxygen atoms. Oh, I can rewrite it then. I'll rewrite it. So just to reiterate the logic, so for nickel 3 oxide, going to nickel hydroxide, first and foremost, I balance my nickel atoms. Then I look at my oxidation numbers. The oxidation number of nickel is +3 in nickel 3 oxide. In nickel hydroxide, it's +2. My delta is 2 minus 3, which is -1. I have -1. I have gained 1 electron per nickel times 2. That gives us 2 electrons gained. And now let's take about 2 minutes and let's try and balance this equation with respect to hydrogen and oxygen atoms. How many hydroxides and how many water molecules do I need to add to each side? And don't be shy to make a have-need table. And let's try to get a few responses in the chat or using annotate. And just as a side note, if you look at your Zoom meeting controls, you'll see this little button with a pen on it called annotate. And if you'd want to share your perspective, multiple students can annotate on the same board. So it's always good if you want to share your opinion and don't want to type it out in the chat, since some of these reactions are a little annoying to type out. So we have the start of a have-need table. So I'll provide some guidance now to help everyone through this process. So we see that we have 4 oxygens and 4 hydrogens on the right, and we have 3 oxygens on the left. Okay, so we need +1 oxygen to the right. Okay, so, +1 oxygen to the left. And 3 + 1 would give us 4. So then we're going to add the following pair of hydroxide and water. That gives us +1 oxygen to the right. And we also need +1 oxygen to the left. We need 4 hydrogens to the right. So then we're going to add the pair of OH to H2O, and we're going to multiply it by 4. Okay, so let's add this to our base equation, and that in turn gives us 2 electrons plus nickel 3 oxide plus 6 hydroxide leads to 2 nickel hydroxide plus 5 H2O. Okay, so here's one of our equations. Let's write our second equation. Cadmium solid plus 2 OH minus leads to cadmium hydroxide solid plus 2 electrons. So now that we have both of our equations established, do we need to do anything special to add them together? Do we need to modify our equations to add them together? Do we need to modify our equations to add them together? Wait. Let's look at this equation one more time. Oh, sorry, this is reversed. We need 4 hydrogens on the left. So we need the following pair of H2O to OH minus times 4. So that gives us the following equation. So we get 3 H2O on the left and 2 hydroxide on the right. So now that we have our 2 equations established, our 2 half reactions, do we need to do anything to these half reactions to add them together? No, everything looks good. We have 2 electrons. Our electrons are balanced, so we just add our equations together. We can cancel our hydroxide, and that in turn gives us nickel 3 oxide plus cadmium solid plus 3 H2O leads to 2 nickel hydroxide solid plus cadmium hydroxide solid. And now, just as our last part of this exercise, I'd like you to check and I'd like you to tell me, is this equation balanced? Is this equation balanced? Yep, it's balanced. So we put a check mark next to it. Perfect. So I know for balancing redox, it's a lot to take in. I have some practice examples prepared on Canvas that you'll see later tonight as well. We'll cap off today's lecture right now, and we'll continue this lecture tomorrow.